we didn't do about the ammeter or whatever that they call it. The problem in the book is exactly like that problem. Okay, so if you just model the problem in the book that talks about the ammeter, you'll be fine. I don't want to waste your time doing that, or really waste my time, because we need to get on to magnetism here. Okay, and this is electromagnetism. Electromagnetic forces they're one and the same. Okay, so if you have, basically it works like this. I'll show you. Here's kind of a demo of electric and magnetic forces at work. Okay, first of all, here I'm going to show you how the actual braking system on like the Mamba works, or the initial braking system. Here's the braking system invented by psych majors. Okay, that is not a good braking system. Okay, but if you give, but what do we call it? But the psych majors and English majors who designed it liked it. You know why? What do you call a psych major or a business major who makes money? A lawyer. So they like that one. Anyway, so because there'd be a lot of lawsuits. So anyway, here's another one. That one works every single time. Okay, how many of you are at Weeblos on Wheels? Did you all use this one? Did you come by? You probably went, I don't know. Okay, so that didn't work very well. Now then, that one worked pretty well. There's probably a reason why that one worked. Oh, I wonder what's wrong. What is wrong with this thing? Anyway, so we'll put it there. So obviously, what does it have? Magnets. Okay, but so what? Because I don't know if y'all can see this, but you see the strip in there? What's it made out of? Can you tell? Copper. All right, now, all of you, since the time you're like 4 or 5 years old and you were first playing like with little magnets and stuff, you tried to pick up pennies and it didn't work, right? Because copper doesn't pick up pennies. However, copper is a good what? Conductor, right? So that means it's like Southwest Airlines. The electrons are free to move about the wire. Okay, so what's that? Yeah, and they'll even take your bag. Right, Jimmy, it's on. But anyway, so as we come down here, so what happens is when magnets move over a conducting surface, okay, when magnets move or when the conducting surface moves, that creates a voltage. That creates an EMF. This is the whole big idea of the next 3 chapters. Okay, so you don't need to write this down. This is kind of let physics flow over you for this first 10 or 15 minutes of class. All right. So what happens is we create a voltage, which creates a current. Okay, so that voltage creates a current, which creates a force. All right, and I use this. Oh no, hold on. Sorry, let me turn that off. Okay, there we go. Sorry about that. Should have put that on silent. But anyway, I'm not used to having this thing on me. But anyway, so when it creates a force, all right, and it's a 3-dimensional thing that we're going to be dealing with. So I'm going to teach you the right-hand rule right now, and we'll look at it later on too. Anyway, all you need to do this mathematics is your right hand. So hold up your right hand. Repeat after me. I promise not to email Mr. Riggs after midnight on when the homework's due. But anyway, no, but hold up your right hand, and this will be the direction of the magnetic field. Your fingers will be the direction of the magnetic field, okay? And when that magnetic field was moving along the copper that way, it created a voltage that was going this way, all right? So your hand kind of creates a battery, all right? And so you stick your thumb straight out. That's the direction of the current. All right, now things have to be moving for that to happen. So, and then what happens is that creates a force that's perpendicular to all that, which goes back. So you just curl your fingers back. So that's how you do it. I think in some of the MCAT things they taught you that you go your finger's the magnetic field, your thumb is the current, and then this finger like that is the direction of the force. Well, I think that gets us into trouble. But anyway. So especially when you're teaching this to junior high kids. They have a tendency to have a lot of fun with that. So anyway, so that's the big idea. Moving magnets, moving magnets make a, so let's go to Faraday's lab. Now here's the first idea that was introduced in your book on chapter 19, okay, which is what we're doing is magnetism. All right, it said that the direction of the magnetic field, if you put a compass in the magnetic field, the direction of the magnetic field will be indicated by the north pointing end of the compass. I don't know if y'all can see this very well, but here's just a simple little bar magnet, okay? And notice the magnetic field is, the direction is the red arrows. Okay, so there's the North Pole and the red arrows are coming out here. And so so if I slide the magnetic field, this compass over here, where it's pointing north will be in the direction of the magnetic field. And then as I slide it around here, in other words, it's going to point to the south end of this magnet the best it can. There it goes. All right, so there's my magnetic field. Now, you might be wondering, well, how the heck why do we have hydroelectric generators? What do they mean by a hydroelectric generator? Okay, we've got, usually it's associated with falling water, which creates a lot of force. Okay, basically falling water is a mechanical energy. Okay, you got all this massive water falling. It's going to hit these turbines. Okay, and these turbines are going to turn. What do you think these turbines have on them? Huge magnets. What's in the middle of the turbine? A big chunk of copper wire. Okay, and so that creates a current. And here's basically how it looks. All right, so here we go. Here's my little, here's my thing. Now I'm going to turn on the hydroelectric generator here. It's going to turn that magnet, which creates a current in this wire. Okay, this moving magnet over here is creating a voltage. It's actually, so what kind of voltage would this be since it's going back and forth? It's AC, right? It's alternating current voltage, and that's what we get in our house. So that's, and the more the more I turn up the water, or the more I open up those floodgates at Bagnell Dam or whatever, the more water I get, the more power I get, more energy. Okay? All right, so those are all the big ideas that we're going to be talking about. What's this guy? Oh, yeah. This guy shows, okay, so nothing's happening here. Nothing's happening. I need to get something to happen. So what I'm going to do is I'm just going to start moving this, shaking this magnet around. And what happens is that moving magnetic field causes these electrons to move. It creates a voltage, creates an EMF, which gets those electrons to move. So when the magnetic field's increasing, the electrons go one way. When it's decreasing, the electrons go the other way. And so that increasing and decreasing of the magnetic field, which is also called the magnetic flux, okay, which magnetic field times area is the flux. And so if that magnetic field increases or the area increases, then that'll create, and it's the change in the flux that we actually look at. Now this is all maybe even up to chapter 20 type stuff. So I'm just giving you the big overview of electricity and magnetism. And now we've got a little video I want to watch real quick. I haven't assigned you a new assignment yet, but kind of expect it tomorrow sometime, and it'll be due. Oh, well, because I'm going to assign you the full bore from chapter 19, so you get the whole, you get a full dose of magnetism. So we'll make it due like Thursday, so that way we'll have class, because we'll finish the chapter Wednesday and Friday, and then, well, if we have little homework questions, we can do it. But anyway, what we're going to do is watch this little thing on, now this is from Brian Greene's The Elegant Universe, where he actually talks about string theory and basically trying to get quantum mechanics and electricity and magnetism and gravity to all talk to each other, but all these theories to talk to each other, but we don't have that yet. Ting-Yi's going to figure it out. That's what she's going to go off and do on when she, but anyway, that's what I heard. Maybe not. All right. So let's go ahead and watch this thing on, basically, this is kind of a cool little thing because we're going to talk about relativity later on in this chapter. It kind of starts with a little discussion of relativity, but then it gets all these physicists start talking about the elegance of electricity and magnetism. So it's just kind of to show you what it's all about. And I can't get this any bigger for some reason.
And a single dimension of time as bound together in a single fabric of space-time. It was his hope that by understanding the geometry of this four-dimensional fabric of space-time, that he could simply talk about things moving along surfaces in this space-time fabric.
Like the surface of a trampoline, this unified fabric is warped and stretched by heavy objects like planets and stars. And it's this warping or curving of space-time that creates what we feel as gravity. A planet like the Earth is kept in orbit not because the sun reaches out and instantaneously grabs hold of it, as Newton's theory, but simply because it curves in the spatial fabric caused by the sun's presence. So, with this new understanding of gravity, let's rerun the cosmic catastrophe. Let's see what happens now if the sun disappears. The gravitational disturbance that results will form a wave that travels across the spatial fabric in much the same way that a pebble dropped into a pond makes ripples that travel across the surface of the water. So we wouldn't feel a change in our orbit around the sun until this wave reached the Earth. What's more, Einstein calculated that these ripples of gravity travel at exactly the speed of light. And so, with this new approach, Einstein resolved the conflict with Newton over how fast gravity travels. And more than that, Einstein gave the world a new picture for what the force of gravity actually is. It's warps and curves in the fabric of space and time. Einstein called this new picture of gravity general relativity. And within a few short years, Albert Einstein became a household name.
Einstein was like a rock star in his day. He was one of the most widely known and recognizable figures alive. He and perhaps Charlie Chaplin were the reigning kings of the popular media.
People followed his work, and they were anticipating, because of this wonderful thing he had done with general relativity, this recasting the laws of gravity out of his head. There was the thought he could do it again, and people want to be in on that.
Despite all that he had achieved, Einstein wasn't satisfied. He immediately set his sights on an even grander goal, the unification of his new picture of gravity with the only other force known at the time, electromagnetism. Now, electromagnetism is a force that had itself been unified only a few decades earlier. In the mid-1800s, electricity and magnetism were sparking scientists' interest. These two forces seemed to share a curious relationship that inventors like Samuel Morse were taking advantage of in newfangled devices such as the telegraph. An electrical pulse sent through a telegraph wire to a magnet thousands of miles away produced the familiar dots and dashes of Morse code that allowed messages to be transmitted across the continent in a fraction of a second. Although the telegraph was a sensation, the fundamental science driving it remained something of a mystery. But to a Scottish scientist named James Clerk Maxwell, the relationship between electricity and magnetism was so obvious in nature that it demanded unification. If you've ever been on top of a mountain during a thunderstorm, you'll get the idea of how electricity and magnetism are closely related. When a stream of electrically charged particles flows, like in a bolt of lightning, it creates a magnetic field, and you can see evidence of this on a compass. Obsessed with this relationship, the Scot was determined to explain the connection between electricity and magnetism in the language of mathematics. Casting new light on the subject, Maxwell devised a set of 4 elegant mathematical equations that unified electricity and magnetism in a single force called electromagnetism. And like Isaac Newton before him, Maxwell's unification took science a step closer to cracking the code of the universe.
That was really the remarkable thing, that these different phenomena were really connected in this way. And it's another example of diverse phenomena coming from a single underlying building block or single underlying principle.
Imagine that everything you can think of that has to do with electricity and magnetism can all be written in 4 very simple equations. Isn't that incredible? Isn't that amazing? I call that elegant.
Einstein thought that this was one of the triumphant moments of all of physics and admired Maxwell hugely for what he had done.
About 50 years after Maxwell unified electricity and magnetism, Einstein was confident that if he could unify his new theory of gravity with Maxwell's electromagnetism, he'd be able to formulate a master equation that could describe everything, the entire universe.
Einstein clearly believes that the universe has an overall grand and beautiful pattern to the way that it works. And so to answer the question, why was he looking for unification? I think the answer is simply that Einstein is one of those physicists who really wants to know the mind of God, which means the entire picture.
All right. Okay, so basically that was a long way to go to get those those 4 little equations, which you do in 250 because those were all differentials, as you saw. But we do the same thing. We're going to do the same thing, just we're going to do them algebraically is all. So basically the next 4 chapters boils down to 4 basic equations, but you're going to get about 30 of them because we're going to break them down into different things. So let's go ahead and get started on what E&M is all about here. View show. So there we go. There's your famous textbook. All right. Here's a circuit set up with this little armature thing in it. Now basically see what they've done is they've wrapped a cord and they're showing the direction of the current going through this cord. That current will create, the other thing I forgot to tell you, moving magnets create a current, but guess what else currents create? They create a magnetic field, as they talked about in here. So there's give and take on both things. So if you create a current, there's a magnetic field that shoots out from that too. Okay? And if you create a current, that's why those little solenoids are used so much. If you create a current inside a solenoid, that creates a very strong magnet on the inside. How many of you, when you're like in 4th and 5th grade, made your little electromagnets with the nail and the 9-volt battery? Did y'all do that? Yeah. And basically what you're doing is, and I don't know if your 4th or 5th grade teacher understood the science behind it, besides the fact that the basic thing, remember, the basic thing is that current going through there created a magnetic field. What it did was, I don't know if you tried it with other things besides putting that nail in there, but what that magnetic field did was it lined up all your little magnetrons. That is not a technical term, but anyway, it lined up the polarity of the iron core that you put inside that thing, which was your iron nail that you put in there. And so since it had polarity, it became a magnet. That's why I was able to pick up things. All right? And we'll get to how that works too. So these are all the things. Chapter 19 is a long chapter, but we'll get through it this week. And it'll be we're going to try and keep it from being too crazy. All right. First of all, magnets have two distinct poles. We refer to them as the north, of course, as north and south. Now, this is what makes magnets different from a charge. Remember, a proton, how many is it? A proton just has a positive charge, right? Electron just has a negative charge. A magnet has both a north and south pole. In other words, it's sending out, remember, the proton sent out an E field in all directions this way, an electron attracted an E field in all directions. Well, a magnet sends out a B field from its north end, and an attractive B field is there on its south end. Okay? So it's a dipole. All right? And nobody has theoretically, you could make a monopole magnet. You could just have it theoretically. It hasn't been done yet in the lab. Now, what would happen if I cut this magnet in half? Whoosh. What's that? Yeah, all of a sudden, if I took it, would I just have a north end? No, it would form a south end. They're like earthworms. You know, you cut them in half, they still live. All right, that's for you biology majors. But anyway, I don't know how many times you can cut an earthworm and it'll still. It depends on where you cut it. On the cut the where? Yeah, there's the earth is slightly rounder.
If
Yeah.
you cut it like right in the middle of there, it won't regenerate. But if you cut anywhere on the other side,
It will regenerate, yeah. Or it'll still be squiggly, and you can put it on your hook. Right, that's all I use them for. That's all I need for earthworms. There you go. Go catch me a crappie. All right, anyway. Now, so, just like charges, like poles, in other words, like poles attract each other, or repel, thank you, and opposite poles attract. Okay? And you can feel a pretty strong magnetic force sometimes in your poles there. Okay. Okay, two magnetic poles of opposite kind form a magnet. Okay, we talked about that. The direction, this is the thing that I want, that's why I showed you that one thing. The direction of the magnetic field B at any location is the direction that the north pole of a compass would point if placed in that location. In other words, to find the direction of a magnetic field of a bar magnet, you take a little bitty compass, and we have all these little kits that we use with the How Things Work students. Why I don't get them out for you all, I'm lazy, mainly. And you can put a little compass by this bar magnet, and you'll see that it'll point in the direction of the electric field. So if that thing points in the direction of electric field, there has to be something happening, right? It has to feel a force, okay? There's definitely a force there, all right? In the magnetic field. This will point in the direction of the magnetic field. Okay, so it definitely has to feel a force. All right. Okay. There we go. They're attracted by each other. And just like your electric field lines, remember when you drew the electric field lines off the positive charge and all that stuff, and you had a couple, and most of you got them all right on the about the electric field is they get more intense. The stronger the field is, the closer the lines are together. Same thing here. Same thing here. Magnetic field lines come off the thing, and the stronger they are, the closer they are together. That's why, how many of you have ever done the iron filings on a sheet of notebook paper, and you put the magnet underneath it, and you plop it on there, and they kind of go whoosh, and they form the field. That's what you're looking at. So basically, you're looking at the magnetic field. Okay. Fun with electricity and magnetism. Another fun thing is to take a really strong magnet and steal somebody's credit card and go like this. No, but anyway. No, you don't want to do that. The reason is, and we'll get, and I'll talk a little bit about that, about all the, how it's all related. You might be going, well, how does that, I've wondered for a long time why a magnetic field destroyed the information that's on the back of that card. Why do they call that an electromagnetic strip? It's because we can store information inside that electric field. Okay? we can store ones and zeros because it's pulsating, stuff like that. All right, it's got a frequency. Okay, now, okay. All right, now here's right-hand rule number 1 again that we're going to learn one more time. Magnetic field goes in the direction of, now this is when everything's perpendicular. Magnetic field goes in the direction of your fingers. Okay, so in this case, magnetic field's going in the direction of the fingers. The velocity of this proton is coming into this electric field. So here comes the proton coming in here. Notice it's a velocity. It's a constant velocity. It is not accelerating. So we'll keep it nice. The calculation's nice and fairly easy. So it's coming in. So which way is the force going to? If the velocity is this way, the magnetic field is going that way. Which way is the force going to go? Up. So it goes whoosh. So it takes off. All right. So if you launch, so that's one of the things we like to do is we like to, I don't know if none of you will be able to see this, but anyway, let's say we've got a, we'll get to the mass spectrometer. We've got an electric field, a B field. Now, we label the electric field with the capital letter B. So you've got a B field going this way, and I'm going to, I fire a proton through here. Okay, so I'm firing a proton through there. It's got a velocity going this way. So again, B field going this way, velocity going that way. So which way is the force going? Oh, I blew it. Drew a stupid force. Which way is the force going on this one? Into the board, right? Because the B field's going that way, velocity this way, so the B field's going into the board. But what we like to do is get things to curve, so they'll go in a circle, all right? And here we go. So here you are. Here is the magnetic field that, here's the way you measure the magnetic field. F equals, the magnetic field is equal to the force that is felt, okay, divided by QV. Or we can say that the force is equal to the charge Q times the velocity of that proton times B. Now then, magnetic field going this way, all right? And let's say the velocity is going, all right, I got a magnetic field going across the room like this, and I'm going to shoot a proton this way. Which way is the force going to go in this case? Up. All right, now, what happens if it's an electron? What do you think, which direction do you think the force is going to go? Down. There you go. Okay, so if it says an electron is going through something, which direction is it going? You'll do your thing for the proton and just have it go in a 180 from there. Okay, it'll go in the opposite direction. Protons, electrons will go in the opposite direction. All right. Somebody's desperate to talk to me. Sorry about that. Okay. In general, the particle is moving at an angle to the field. Okay. Now this previous formula only works when it's perpendicular. All right. But this formula, where F equals QVB sine theta, in other words, you take the if the electron is moving like, oh man, that's going to be terrible. Let's try this. This one might work a little better. All right, let's say the electron is moving. Oh yeah, that's somewhat better, except that they have no clue. All right, let's say the electron is moving like this in a magnetic field that's like this. Okay, and so it's hitting this magnetic field at this angle theta here. All right, and so that's when we take that sine of the angle. It's only the perpendicular part of the field that's affecting it. Okay, not the parallel part, only the perpendicular part. This is why, and this will probably be one of your multiple choice questions, this is why the magnetic field does no work, unlike the electric field. It can't do any work because on a proton or an electron because it's always perpendicular to it. And remember what work is. Force times distance, the parallel thing to it. And so a magnetic field can do no work. All right, it's kind of like the tension in a string when you're swinging. The tension does no work. Gravity does all the work when you're swinging because it's pulling you down. That's the part that perpendicular part that's pulling you, or that parallel part that's pulling you down is doing the work, but the perpendicular part that's keeping you swinging is not doing any work. Okay. Okay, the force is perpendicular to both the velocity and to the field. And we've already looked at that. So it's a three-dimensional thing. Here's your right-hand rule. They give you 4 different ways of doing the right-hand rule. Okay? All right. Okay. All right. Wow. 9.3. We're already up to 19.3. I think I'm going to have to shut this down, and we're going to have to look at some examples so that you all can get an idea of what's going on. Okay. Because this looks really confusing. A cathode ray tube such as a television or a computer monitor uses a magnet to direct a beam of electrons. Okay, so you got this beam of electrons to different spots on the fluorescent screen, creating an image. That's basically what's going on. Okay, so until Maxwell wrote his equations, we couldn't have any television. Of course, we didn't have any television until almost 100 years after he wrote all his equations. All right, well, 60 years. Okay, all right. So that's what they do. Okay, now, here we go. Here we go. Notice we got an E field that's going like this. We got this electric field. This is kind of a cool, this is the way those particle accelerators like at CERN work, except that their magnets that they're using are 22 meters high and things like that. Huge amount. Uh-oh. What's the unit for magnets, for a magnetic field? What was the unit? Teslas, right. Teslas, right. After, y'all heard of the Tesla coil? That thing that kind of like shoots sparks, gets a tremendous amount of voltage and shoots sparks out into the air. Tesla was a Serbian inventor. He worked for Westinghouse. Actually, he worked for Thomas Edison, and they had a big falling out. And in fact, Edison might have stolen some of his ideas and patents. But anyway, they had a big falling out because, and my friend Mike Kelly's going to come give you all a lecture on the whole grid and how all that works. But anyway, basically Tesla wanted, the whole thing was, how do we move this massive, this very productive energy, how do we move it and control it so that we don't have, so that we're not dependent upon kerosene anymore and all that kind of stuff, okay? And Edison's idea was, well, we can just put a DC power station on every block in town. And Tesla was like, well, wait a minute, that's not going to work very well for the people out in the farming country. And unlike today, where it's 70-30, back then it was 30% urban and 70% rural. Anyway, and so the AC is what won out. But anyway, what we have here is we got an electric field coming like this. Okay, got an electric field. Now, if I shot a proton, is that what we're doing here? Are we shooting an ion? Yeah, we're shooting an ion, so that's a proton, right? It's got a positive charge. We're shooting this thing with a positive charge. Now, if this B field was not here, what would happen to this proton as it entered this electric field? It would bend towards the negative, right? But now, here's the second thing you need to know. These crosses, which way is that saying the B field is going, the magnetic field is going, when it's got a cross? Do you know? It's going into the paper. So you think of things, so you think of those directions that are drawn like that. You think of those directions like an arrow. If you shoot an arrow, you're going to see the feathers, right? It's going to be going away from you. You're going to see the feather part of it. I'm not a archer, so I don't know what that's exactly called. But anyway, so you're going to see the feathers. However, if you happen to be the target of an arrow and it's coming at you, what are you going to see? Just the point. All right? So this means coming out, and this means going in. Okay? That's coming out. This is going in. So let's try and figure this out. Okay, so the particle, if it was just the E field, would want to go like this, would want to curve down. But now that we've got this guy going in, velocity going like that, which way is the force going? Up. It's going up. Okay, so therefore, the two forces are countering each other. Okay, you got one force, the good old QE force, which is the force that the charge would feel once it hit that electric field. That QE force is equal to the QVB force. These two guys are equal to each other. So QE equals QVB in this case. And what's going to cancel? When you set the Q's. So the electric field equals the velocity of the electron times the B field. That's kind of weird. That would be a fun thing to figure out. How the heck can newtons per coulomb equal meters per second per Tesla? Well, that'd be a good little problem to do. Anyway. Well, what did we say Teslas were? Teslas were newtons per coulomb meters per second. Or actually, they're actually newton seconds per coulomb meters. Right? Yeah. So it'd work out. Anyway, so given these values, the electric and magnetic field, there will be a single velocity that will allow ions to pass this detector this way. V equals, what is that? The voltage. Exactly. The voltage equals that B field times the distance between the, thank you, the distance between the two things on the capacitor. Okay. All right. With trepidation, I'm going to go to the next slide because I didn't think we'd get this far. I didn't want to get this far. So but oh yeah, I did want to get just this far. All right. So when that guy enters that B field, all right. So let's get that picture of the electric field out of there. We don't have an electric field anymore. We're back to this idea where we've got an electron shooting through a B field perpendicular to it, and it's going to go in a circle. When it goes in a circle, does it feel a force? Yeah. In fact, as it goes in that circle, it's always going to feel a force towards the center of that circle. And we've seen that before, right? Where we've got that. Yeah, exactly. It's the centripetal force. The centripetal force, Fc, equals mv squared over r. So you've got mv squared over r also equals that QVB. So you got mv squared over r equals QVB, and that's how they derived this guy. All right? And we will stop there. You guys have been hammered with a lot of information this morning or this afternoon. And what we'll do is I'll publish, I'll get you your homework assignment out there by tomorrow, and then on Wednesday we'll go over the first 3 or 4 types of problems that you'll encounter so that you can do them. Hi, Melissa.